Hi everyone, welcome to our chapter 3 on probability. Probability show up everywhere no matter your field. For example, in business, we use probability to estimate the chance of success of a new business in the market. In engineering, we use to measure the reliability of systems. For example, the chance of a bridge or machine part still hold up under stress. In technology, we use to power algorithms that recommend music, movies, or detect spam emails. In this chapter, we build the tools to calculate and understand these chances, starting with very simple ideas like coin flip or dice, and then moving toward real-life applications. So let's hop on. So now let us discuss the definition of probability in a more official way, and we learn the basic rule to calculate probability. So let us look at some terminology first. Um, the first terminology is a random phenomenon. It's a phenomenon with outcome random. So for example, if you toss a die, right? So you know that the outcome can be 1, 2, 3, 4, 5, 6, but for sure you don't know in advance which one going to be landed, right? I say a random phenomenon. Another one is whether it rain or not in the next month. So which is exact, 30 days after today. So you know that it may rain or not rain, but you don't know for sure what the outcome is going to be. So all these phenomenon we call random phenomenon. In the sample space, it's just the space of all possible outcomes. So in the case, say you toss a die, the sample space will be 1, 2, 3, 4, 5, 6. And if we talk about rain or not 30 days from now, right? So with the sample space, maybe rain or not rain, right? So if you classify in the two classes. The event which is a collection of outcomes, and we denote it by A and B, which is capital letters. So for example, like if we toss a die, we can consider the event where the die will land on even phase, right? Maybe 2, 4, 6, or odd, right? 1, 3, 5, a prime number, which is 2, 3, and 5. The symbol event is the outcome event cannot be further broken. So for example, if you toss a die, the symbol event will be 1, 2, 3, 4, 5, 6. But say if you consider the event like the face landed will be an odd number. So this event is not a symbol event because it can be broken by 1, 3, 5, right? The complement of an event, which is the event that include all outcome not in the event we are considering. So, for example, like here you can see like if you consider event toss a coin, you get an odd phase, right? So the complement will be the even phase, even phase. I say if you have a newborn baby, event A, the event a newborn baby gender is the male, right? So the complement of it is female. And often we denote it by the event itself, and we have a bar on the top, which represent for the complement. Experiment, it is a process that can be repeated in which results are uncertain. So say like I want to know that whether my coin is fair or not, right? My coin is fair or not. And then basically I can do an experiment is that I toss a coin 100 times and I track the number of heads, right? Heads. So this is the experiment I do. I toss and I track whether head or tail. I toss again. I track. I toss again. I track. Right. I say the same thing for the die. Right. So say if you have a die and right, and you want to know you have fair die or not, and you can conduct the same experiment. Right. You toss it maybe 100 or 1,000 times, and you keep track a number of each phase show up, right? And if we have a fair die, which means you should expect the chance, each phase show up will be relatively the same. And then a probability, and from now on we will use a abbreviation prob, P-R-O-B. This is just a measurement to quantify the likelihood of events, and we denote it P. Okay, P. So basically, like if we get an event and we actually we really want to know what the chance of that event happen, right? Uh, and that is called probability. How likely it's going to happen. So here, let's say, you have event A, right? And you do care about what the probability of A happen. And we denote here by PA. And the probability is a number between 0 and 1. It must be between 0 and 1, okay? We don't have negative probability. We also don't have a bigger than 1 probability. If you have a probability of 0, which means the event A cannot occur, impossible to occur. So say again, say, if you touch the boiled water, right? Say, and for sure, the event is, if I consider A the event, that you won't get burned, right? So PA will be 0, right? Because if you touch the boiled water, for sure you have to get burned, right? Get burned. So the PA, if you consider A the event, you don't get burned, the PA will be 0. And say if I consider B the event, you get burned, right? And other time, your PB will be 1, right? Because you get burned for sure if you touch the boiled water. And this is a fact, right? Everyone know. And say if we have a B event in lower side, say, if you consider event A, and its probability close to 0, and less than half, right? And basically uh, it's will less likely to happen. And also vice versa. If you have the size which is bigger than half, which is belong to the size it's likely to happen. And if you have an event with probability half, which means you have 50-50 chance. And here we have another example. If I event A, and the probability of you have PA 0.167, so which means the likelihood of this occurring event A is 0.167, or if you talk about percentage, about 16.7%. So in this example of 3-1-1 here, you see you toss a fair die, right, of 6 faces. And A is the event that you get face number 7. So which means in that case, impossible, right? The PA 0. And say B is the event you get a face less than number 7. And for sure, you get that event 1. Because you toss a fair die, which is a normal die, right? You have the number on the face as 1, 2, 3, 4, 5, 6, 7. So the PB will be 1. And if you already know C, the when you get a face 1, number 1, so the chance you get this event is 1/6. Given that we have fair die, okay? So you see in this chapter, we will use the example of coin and die a lot because it's intuitive. And for sure, we can extend it to more complicated setting, but I believe this use of coin and die will make things clearer for all of us. And eventually, we can move on to more complicated setting, okay? So here we look at another example. We consider infant gender, okay? So if you consider random phenomena, you're curious about what the gender of two newborn, two newborn in the hospital, maybe Orlando today. And then basically the sample space we have will be the possibility can be boy, 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 girl, girl, boy, or girl, girl, right?
this is sample space. And say if we talk about event, say if you already know A is the event that you get the same gender. And other time the event B A it will uh, can be boy boy or girl girl, right? And if you already know B is the event we have different gender, and then the event B can be the first baby is boy, second is girl, and or the first is girl and second is boy. So yeah, B will be boy girl and girl boy, right? The symbol events in this random phenomenon, it can be uh, boy boy, boy girl, girl boy, or girl girl, right? And they are all symbol events. And if A is a same gender event, right? So BA basically is just a property you have in the same gender, having the same gender. And we can calculate that, right? You can look at it. But now let us just look at some other uh, some approaches people use to define probability. So for approaches to define probability, we have a different way to look at probability. One approach we call subjective probability. So this is a subjective matter. Actually, we do use it a lot in our daily life, right? Daily life. So say for example, like John, right? He kind of Star Wars fan, right? So he may think that probably if he's seen an lion tonight is point 0.9, right? But Mary, she not a big fan of Star Wars, right? So she think it's 0. In the usage here, it's commonly used in our daily judgments, right? Uh, we have our own subjective on each matters of this life, right? And often, the more experienced you are, uh, the better judgment you can give to things. Uh, the approach number two, which is we call classical approach, classical probability. So we define the probability of event A is just a ratio of number of time A occur and divide by the total of number of symbol events, or just a sample, or the sample space, the size of the sample space. And the requirement to make this approach work is that we require all symbol events have the same chance happening, the same chance happening. And the usage here is often very common in gamble testing or illustrate properties. So for example, like coin, die, right? All thing it makes sense where you have fair coin, fair die. So if you look back at the infant gender example, right? So you see here, like if you consider A the when you have the same gender, right? So what the probability you get the two baby with the same gender? So in order to calculate this probability, what you need to do is that you need to find out what the size of sample space here. So in this case, the sample space we get boy boy, boy girl, girl boy, and girl girl, which you have sample size 4. And the same gender is boy boy, girl girl. So if we assume that all these things occur with the same chance, right? Boy boy, boy girl, girl boy, girl girl, which means you assume that the gender of the newborn baby, boy or girl, is 50-50, right? So if that's the case, and basically like you can calculate the PA, which you count the number of A occur here, A, right, the size of A, divided by the sample size here, which is 2 divided by 4. So here A, you have two events, right? Um, two cases, right? Two possible outcomes, and here you have four possible outcomes. So basically like PA will be 2 by 4 or half, right? So probably you got like two baby with the same gender, a half. So this is the example. You can see that. And then another approach, which is the most commonly used, we call relative frequency of probability. And this approach is defined by, if you want to calculate probability A happen, what you need to do is that you need to track number of time A occur and divide by total number of trials. Um, and this happen if you can repeat the trial many times, right? But in reality, often we use it, the approximation here come from the empirical data. So for example, like if you care about what is the probability of a student take my class in Math 100, right, and pass this class. So one strategy you can do is that you can look at the past data, right, and you say, okay, we got like 300 students enroll in my class, and 270 students pass, right, pass. So from that, you can give a rough estimation. The probability of taking my class and pass is 270 divided by 300, in which is 0.9, right? 90%. And it's the most commonly used in real world and study. Maybe because like nowadays you see people can keep track of the tremendous amount of data, right? In a very timely manner. So now let us look at the law of large number, which is one of the most important law in probability. Law of large number say that it tells us the relative frequency probability of event will tend to the actual probability if you have a large enough number of trials. Okay, so when you have a large enough number of trials, thing will converge to the underlying truth. So say, if you have a fair coin, right? And if you want to know whether it's fair or not, right? Which means you should expect like the probability of a head is in a toss, right? It half, right? So in order to do that, one way we can do is that we just keep tossing, right? Many times, right? Many times. And from that, you can keep track number of heads among the total number of toss, and from that you can confirm either fair coin or not. So here, like some historic data, where some people, some professor, long time ago, they did this experiment. So for George's Leclerc, he in 1800, he did toss 4,040 times with his coin. Okay, and he find out that it's he got about 2,048 head. So which you see if you do this ratio, you get about 0.5069. So it's pretty close to zero point 0.5, right? And Carl Pearson, he one of the most famous statistician in the world. I believe he is one of the two, right? Father of statistics. He is in early 20th century. He did 24,000 toss, and he got like 12,012 head. And you see, it's if you do the ratio, it's about 0.0505, which is even closer than to the 0.5. And then from here you can see them for their coins, both of them we get the value converge very close to the half, right? Which is what we expect for a fair coin. And then here another very important rule which we use to make decision in statistics world, we call the rare event rule. So the rare event rule it tells us yeah, if you have an assumption, you agree with a certain assumption, okay, and then to verify the assumption, right? Basically, like you will collect data. But if you go ahead and collect the data, and the first time you see that the data has some kind of weird property, uh, which very unlikely to occur if your assumption is true. So if that's the case, and then you can conclude that the assumption here probably incorrect. Probably incorrect. And so this is the main logic to make statistics work. Okay, and we use the rare event rule. And sometimes we say like if something rare, it shouldn't happen in the first try, right? In the first try. So here, like you can see the assumption here, like say, if you have fair die, right? So you have fair die. And how to confirm you have fair die, you can toss, right? But say if you toss it 100 times and you find out that 98 times you got a 6. So which means like this will be unlikely to occur, right? If you have fair die. Because you have fair die, the number of 6 happen should be around 16%. It shouldn't be 98% like this. So which means like something wrong with this die, right? Die. And actually we use the rare event rule in a lot of setting in real life, right? So for example, in job interview, right? You assume that this is a good candidate, right? But the first time he got a job interview and he showed up late maybe 15 minutes, right? So I mean, if a person is a good match, a good candidate, they shouldn't we shouldn't see such a thing, right? We shouldn't see such a thing. It will be very rare. He may go to the interview earlier, right? Show up earlier, right? Um, and I mean, the first impression. So, and he show up late. So, which means like maybe the assumption I make he's an excellent candidate, uh, not true, right? And then maybe say if you interview a little bit more, deeper, right, level, right, ask some more question, and he also answer not so good, right, not so fluent, and in which mean like I can confirm that I will go ahead with other candidates, right? And we do use this rare event rule a lot in our daily judgment too. So now let us look at probability rules where it will help us to calculate probability. Okay. First, we have the OR event. The OR, which is the event that occurs that if either A or B occur. Okay, and we didn't know by A union with B, sometimes we call A cup B. Okay, A cup B, the OR event. So you can look at this figure, right? The first figure on the top here, A is the first oval and B is second oval, and A or B will be the shaded section, right? Or shaded section. And the second event is an event or A union with B. Sometimes we say A cap B. Okay, A cap B. This event occurs if both A and B occur. And you can see the second figure from the top right, second one. So you see that A and B here, and basically you have like the A and B, which is the shaded area, which is the common thing of A and B, right? Other complement, which is the A bar here, which is in this case just the opposite of A, right? So say here the sample space is the S, the rectangular here, the whole region S here. And the complement A, which is the pink one, which is in this case will be a yellow, right? Yellow complement. Disjoint event are the event which they don't have any common outcomes. Sometimes we also call it a mutually exclusive event. So in the last figure here, you can see that the number 4 figure here, you see the A and B, they doesn't have anything in common, right? They're disjoint. So for example, you toss a die, right? The A the event you get a odd, B the event you get an even. They will not have anything in common, right? So after we went to this term, right? Now let us just look at how these terms can help to create new events. So say if you draw a card from a 52 card deck and A when you get a heart, right? Maybe 2 heart, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, right? And Ace. On B is when you roll in a spade, and C is when you roll in a king. Okay. So if you look at A and B, A roll in heart, right? A or B, I'm sorry, and B roll in a spade. So A or B, so will be the event either you get a heart or spade, right? Either A and B is the event you roll in a heart in a spade. So which means in this case, you don't have anything, right? Because a card you draw, it cannot be both, right? Be both. And a bar, which is a common A, in this case, we say not drawing heart, right? So it can be a spade, a diamond, a club, right? In this case, you see, because A and B, A is drawing heart and B is drawing spade, and they have nothing in common, right? And we see A and B are disjoint. So let us look at the addition rule. It helps us to calculate the probability of the OR event. So probability of A or B will be equal to probability of A plus probability of B and subtract for A and B. So if you look at the figure, the top figure here on A and B, A or B event, so you can see like we have the first circle here is the A event. The second circle here represents for the B event. A or B will be the shaded area, right? A or B, which is the event we consider on the left-hand side of the equation here. So you can see that the shaded area here, it will be equal to the A area, right, plus the B area. But there's something overlap here, right, which is the join, the intersection, right, of A and B. So the shaded area is equal to the A plus the B, but you also need to subtract the overlap. And the overlap, which is the join of A and B here, which is the A union with B, right? A cap B, right? So this makes the additional rule, right? So you can see it in a geometry way. And for special case, when A and B disjoint, and it becomes marvelous, right? Because you have the intersection be empty set, which means that probably is zero, right? Zero. So basically now you have a very nice formula, PA or B equal to PA plus BB. And also you can see that for A and A bar, right, which is the column A, two of them will make the whole sample space, right? So which means that we have the probability A plus probability A bar will be 1. You can also see that we can find the probability A bar, right, by using probability 1 subtract, by using 1 subtract the probability A. So now we revisit example 3-1 here, and we can start to calculate different probability. Okay. So say if you consider A when you roll in heart, B when you roll in spade, and C roll in a king. So you can see that you can calculate the probability you roll in heart, right? Just by using the classical approach, right? So here in draw and heart, you can see that you have 13 possible cases, right? Because you have 13 cards, and each card can go with can get heart, right? So the probability is will be 13 divided by a sample space size is 52, right? Because in the card we got the deck we got 52 cards, so it'll be 13 by 52, and if we do the calculation, it will give us like 0.25. on 25% if we prefer percent. But for probability, often we use a number between 0 and 1. And B, row and spade, similar, right? You got 13 cases, you get a spade, right? 2 spade, 3 spade, and so on, right? And this probability also 13 by 52. And C, you row and a king, and you see that in a card you got 4 king, right? 4 king. So 4 possible cases. And again, the sample size is still 52. So you can get a PC, right? And how about A and C? A and C draw in a heart, and C draw in a king. So A and C basically is a king heart, right? So this property is at 152. And so on. You can also calculate other probability. How about A and B? A and B, which we already discussed, right? Draw in a heart and draw in spade, which is impossible to happen, right? A card, it cannot happen by both, right? When you draw it, either heart or spade, it cannot both, right? Um, it cannot be both, right? Maybe heart, maybe spade, maybe none of them, but it cannot be both. How about A or C? So A drawing a heart and C drawing a king. Okay. So at that time, if we look at the event in an explicit way, it's doable, but it start looking complicated. Okay, a heart or a king. So you need to list all heart case, all king cases, right? But luckily, with the addition rule, you can look at it and it helps analyze much similar. So here, like BARC, which is your addition rule, which is PA plus BB subtract to ARC, right? PA plus BC subtract to BA and C. So we have to do a little bit modify because it's formula for A or B, right? So after we do that modify, right, you can see that A is 13 by 52. We already got it, right? C, 4 by 52. And A and C, which is 1 by 52, right? And you just plug in and you can get it. It's a 16 by 52 or 0.308 if you keep 3 digits. And column A, which is not drawing hard, just 1 subtract A, right? And then you got 0.75, 0.75. So this example, it gives us, how to apply the basic probability rules to start calculate more complex event. And in this example, right, when we look at this, we can see A or C is event is start to make it analyze complicated, right? And we need the rule to work on that this complex event more efficient, right? So here, like another example, if you roll in a fair die, and here in this case, a sample space will be 1, 2, 3, 4, 5, 6, right? And if I consider A is the event, I got the even phase 2, 4, 6, and B the event when I roll a die, I got 1, 2, 3. Okay. So from that, for sure, you can also list out, right, what is A or B, which in this case will be 1, 2, 3, 4, 6, right? So we should remember we don't double count, right? Double list, relist the thing we on list. So in this case, we have two, the same for two sets, but for the OR event here, we will remove the duplicate. Okay. A and B will be 2, right? A complement, which is whatever not A, right? So we have 1, 3, 5. You can also get B complement. In the same, you can also calculate for all these probability, right? PA, BB, BA bar, right? Which is complement A. But look at the number of outcome in the event, right? So PA here, A, you have the 3 cases, right? 2, 4, 6 divided by sample space size 6, right? So PA will be 3, 6. The same for B, 3, 6, and the same for A bar, right? 1, 3, 5, which you have 3 cases. You have 3, 6. B bar is the same, right? A and B, you have 1 case, which is number 2, right? So the probability will be 1, 6. A or B will be 5, 6. So here, like we calculate this by just list the event explicitly. But again, there are way for us to calculate by look at using the rule, right? So for example, A or B, right? If you don't list A or B explicitly here, you can also use the addition rule, right? PA plus BB subtract PA and B, PA 3, 6, BB 3, 6, A and B 1, 6. So which means in this case you have 5, 6. And same thing, the same thing, right? You can also get a PA bar by equal using like 1 subtract PA. And you also get 3, 6, probably B bar, complement B. So there are different ways to calculate probability. We have to be flexible. And a lot of time, if we can apply the formula, right, and it will make our life much easier. Because it's sometimes listing now all the possible cases, it will be very painful. Okay, very painful, and sometimes it's pretty much impossible to do that. So here, like, let's look at this quiz for a little bit. Okay. So here, Julie draws like one card. Okay, from 52 card deck. Okay, so the same thing. We use a card example, and because symbol, and everyone know that. But for sure, we can always make it more complicated. So 5 probably the card is a queen and heart. And then queen and red, queen or heart, queen or king. So we have 4 questions, right? So let's think about it a little bit. So we have a 52 card deck, right? So queen and heart, which is an event, right? So basically it's just a queen heart, right? So which is event just like one possible case, right? Queen heart. So this probability will be queen and heart, right? And heart. Maybe queen and heart, right? Again, you know this by the A event as well, but here I write for short. Maybe just 1 divided 52, right? 52. Because you just have one case here, queen heart, right? So which means if you didn't know this event, so this will be just like queen heart, right? That's it. Among 52 cards. So queen and red, queen and red, right? Queen and red, right? So this probability is what? 2 by 52, right? So even I know the event is event B, so I can get either a queen heart, right? Or the queen diamond, right? Diamond. So which is 2 by 52. We can do the calculation and get the decimal if we want. Queen or heart? All right. So for sure you can list it, right? You can list it if you want. But here I will use the addition rule because I believe it gives me a faster track compared to list all the event here. With queen or heart, it will not be efficient if you list it. Okay. But what I'm going to do is that I just use queen plus heart, right? And subtract for property of queen and heart, right? So probability of having a queen will be 4 by 52 because you have 4 queens. The heart, you have 13 hearts, you have 13 by 52. And subtract queen and heart, we just calculate in part A, right? 1 by 52. So here you have like 16 by 52. So the card is a queen or king, right? Queen or king. So again, for sure, if I want to list it, I can list it. And it's not a too complicated setting. But I also want to use the complement rule because I think my life is easier if we use that. Uh, Addition rule, I'm sorry. Queen or king, right? The same thing, queen plus king, subtract queen and king. King. Right? Probably a queen, we have 4 queen for 52. Probably a king, we have 452. And queen and king, which is impossible event, right? It cannot be that way. So which is 0, 52, 52, right? So here we use the complement rule, the addition rule. And for this part, actually, it's just a special case, right? Because A and B disjoint. So if you consider A is the event you got a queen, and B the event you got a king, right, in your draw. So they have nothing in common, right? We cannot have the thing happen to at the same time, right? So it's just PA plus BB here, which is special case. But you can also look at the general formula for the addition rule, and you can also see that